Alright, in this video we study the notion of maps and functions. When we study a set, when we are interested in some things, then we collect them to form a set. We define a set, and to study that set, we compare that set with another set. Okay, that's how we can study some set. Okay, so by comparing, we mean defining a map between a set. So, for example, if we have a set A and we are interested in it, then we have another set B. Assume we have another set B and we define a map between them. Let's call that map F. So what is a map? Map is a rule, a set of rules maybe, that assigns an element of B to each and every element of A. So for every element of A, we have some element in B such that f of A is equal to B. Okay, so this defines a map F. Okay, and this set, which is the source of this arrow, is called the domain of the map. Okay, so this is called the domain, and this target set, B in this case, is called codomain. Domain of the map. Okay, so sometimes we write dom of F is A, and codomain of F is B in this case. Let's see a simple example. Let's define a function from the set of integers to the set of natural numbers. Okay, so in this case, f of x, where x is an integer, let's define it as 1 plus x squared. Since x squared is positive integer, then so it is a natural number. So if you add 1 to that natural number, it is still a natural number. So indeed, this output value is a natural number. So in this way, for every integer, we assign this value, 1 plus x squared. So this defines a function or a map between integers and natural numbers. And in this case, the domain is the set of integers, and the codomain is the set of natural numbers. For any set, we can define a special map that is called identity map. This is a very trivial map. So if A is any set, okay, we can define the identity map of the set A as this, where X is any element of A. So in this case, the domain and the codomain are the same set A. Okay, so this ID A has domain A and codomain A. Or maybe you can write like A to A, like this. So ID A. So this can be this map can be defined for any set. So this domain and the codomain set A can be the set of natural numbers or integers or whatever, or set of elephants. You can use any sets for A. Let's see a few more examples of maps. Okay, example. Let's define a function from the set of real numbers to the set of 0 and 1 in the following manner. That is, f of x, of course x is a real number, is equal to 1 if x is a rational number and 0 otherwise. That means if f of x is 0 if x is irrational. Okay, so this is also a function, although this is a very ill-behaved function, but still it's a valid function. And so we can define a function in this way, like using cases. Here's another example. You know the absolute value of x, right? This is also a function. We can write like this. F of x is the absolute value of x, and f is from real numbers to real numbers. Okay, so what is the definition of the absolute value of real numbers anyway? So if you remember, this was defined in this way. The absolute value or modulus of a is equal to x if x is greater than or equal to 0 or negative x otherwise. That means if x is negative, right? So again, this function is defined in terms of cases, two cases. Okay, so many students just have forgotten this definition, so let's review this a little bit more. So for example, the absolute value of 3, according to this definition, this 3 is positive, right? Therefore, we have just 3. And negative 3, this negative 3 is of course negative, so we put negative sign and then take that number inside out. That becomes positive 3. Okay, either case is positive. Of course, the absolute value should be positive or 0. So that's how we define absolute value. In other words, the absolute value represents the magnitude of the number. Okay, so if we plot numbers on the number line, let's say this is 0 and this is 3 and this is negative 3, what these absolute values represent is the distance between the origin and that number. So this length is 3, right? This length is 3 in this case. So we just ignore the sign, the direction on this number line, and just measure the distance. And that is what the absolute value represents. Next, we introduce the notion of image. Okay, so suppose we have a map f from A to B, and then the image of f, which we write as Im of f. And sometimes we might want to put parentheses around f. So this is called image, and it's defined as follows. It is the set of values of f where A is in A. Okay, what does this mean? So we have two sets, obviously, A and B. So let's write it like that, A and B. So for each element of A, we have a corresponding element in B, right? So according to the definition of the map. So that means the entire set A is mapped inside the set B, right? So everything here is somewhere in B. So it forms a subset of B, and that is the image of F. So this image of F is a subset of B, right? So, you know, by the definition of a map, we do not say that every element of B must have a corresponding element in A. That's not a part of the definition of a map. All we say is that every element of A had some corresponding element in B. Okay? Therefore, there may be some elements in B that do not correspond to any of the elements in A. So in that case, image of F becomes a proper subset of B. Of course, sometimes image of F may match exactly to the set B or codomain, but that is a special case. Sometimes the image of F is written as this when A is the domain of F. Okay, so it's the same thing. Okay, so let's see an example. Let's define a function f from the set of natural numbers to the set of real numbers by f of x is equal to x. Okay, so this is almost like the identity function, but it's not, because the codomain and the domain, they are different. Okay, so in this case, the image of f is naturally, it's a natural number, of course, which is a subset of the set of real numbers. And another simple example, let's define f from real numbers to real numbers by f of x is equal to x squared. Okay, in this case, what is the image of f? Okay, of course, you should be able to plot this function on the plane. So x and f of x, it looks like this. It's a quadratic curve, very simple. So this can take only non-negative values. So the image of f in this case is any real number. Let's write it as y. So okay, maybe it's easier if we write like this, and x is a real number. So this is according to the definition, and this is actually equal to, since x is a real number, square of any real number is non-negative. So y greater than or equal to 0. So this set and this set, they mean the same thing. Okay, so in this case, the image of f is the set of all non-negative real numbers. Of course, this is a subset of real numbers. It's a proper subset. We say that the image of a function or a map may not cover the entire codomain, but when it does, it has a special name. So suppose we have a map from A to B, and if the image of f is equal to B, which is codomain of f, if this is the case, then we say f is surjective or is a surjection or onto. Okay, so there are 3 ways to call it, but what this means is clear. So if we have 2 sets A and B, by this map or function f, the image covers the entire codomain. So that's surjective or surjection or onto map. Okay, let's see an example of a surjective map. Let's define f a function f from the set of integers to set of natural numbers by this rule. F of x is equal to 1 plus the absolute value of x, where x is, of course, an integer. Okay. Since x is an integer, the absolute value of x is a non-negative integer, but we add it to 1, so this is a natural number, and every natural number can be expressed in terms of this form, right? Where x is any integer. Therefore, this is a surjection. Okay, so you can actually prove that this is a surjection. So let's say n is any natural number. So can we find an integer? Okay, in any natural number. Okay, so can we find some integer x such that this holds? Of course, it's possible. So, for example, from here we have x is equal to n minus 1, so x is equal to plus minus n minus 1, right? So either negative of negative n minus 1 or positive n minus 1 can serve as this x. So two values of x are mapped to the same natural number. Okay. So this is a surjection. Okay, in this example, two values of integers are mapped to the same natural number, right? So this, for example, negative 3 and positive 3, they both are mapped to the same value, 1 plus 3, that is 4. Okay, but in other cases, no two different values are mapped to the same value. Okay, that is also a special case of a map, and that map is called injection. So let's define more formally. So suppose we have a function or a map from A to B, and we call it this is injective, or an injection, or one-to-one. If and only if the following applies, holds. That is, for all A and A prime in A, if A and A prime are different, then f of A and f of A prime are different. Okay, so if this holds, then we say this map is injective, or it's an injection and injection, or one-to-one. Okay. Or another way to say this definition is that if f of A and f of A prime are the same, if they are equal, then it is necessarily the case that A is equal to A prime. Okay, this is the contrapositive of this statement. Okay. So graphically, if we have A and B here, and if A and A prime, if they are different, then they go to different elements in B. Okay, or if they happen to be the same, okay, in the codomain, then this A and this A prime are actually the same elements. Okay, this cannot happen in injection, or if this doesn't happen, then it's an injection. Let's consider a few examples. Suppose we define a function from real numbers to real numbers by f of x equal to, let's say, 1 plus x cubed. Can you draw the graph of this function? If you draw it, it should look like this. X. And when x is 0, it's 1. It's 1. And otherwise, it's just a cubic function, so it should look like this. So for every value of on the y-axis, there is only one value of x that come to it. Okay. So this is an injection, and this happens to be surjection too, right? So every value of every real number on the y-axis had some corresponding value on the x-axis. So the codomain is entirely covered by the image of this function. So therefore, this is also a surjection. Okay, how about f of x is equal to x squared, and f is from real to real? Is this an injection? Actually, it's not an injection, because if you plot the graph, so for some values of y, we have two values of x corresponding to that y value, right? So therefore, it's not an injection. However, if we limit the domain to only the positive side, let's say, let's define R plus as real numbers that are non-negative. Okay, so if the domain of f is limited to non-negative real numbers, then is it an injection? It is an injection, because here we do not consider the negative x. So for every value of y, we have only one corresponding value of x, right? So therefore, this is an injection. So this shows that whether a function is an injection or not depends on the domain. Okay, if we change the domain, then it may be injection or not injection. And furthermore, by the way, this is not a surjection, right? Because for negative real numbers, there is no corresponding value of x, right? No x can give rise to a negative f of x, right? So this is not a surjection. But again, if we limit the codomain to the non-negative real numbers, then we do not consider the negative part of y. Therefore, for every element of the codomain, we have a corresponding element in the domain. Therefore, it becomes a surjection. So regarding surjection also, it depends on the choice of the codomain. So we have seen that some maps can be either injective or surjective, or actually they can be both. If they are both injective and surjective, then we call it bijective. or bijection. A bijection. And we've seen some examples of bijections already. Next, we consider the graph of a map. For example, if f of x is x squared from real numbers to real numbers, we can draw its graph like this, right? But what is this graph anyway? Or what is the graph in general anyway? So for general maps, the domain and the codomain may not be numbers, right? So we may not be able to plot like this, but we can still define the notion of the graph of that map. So how do we do that? So let's say we have a map from A to B, map F from A to B, then the graph of F is defined by this set. It's a set of pairs A and B such that A is an element of A and B is equal to f of A, right? And this is actually a subset of the Cartesian product A times B. So this is how we define the graph of a map in general, okay? And this definition actually matches what we usually take as a graph, like this one, okay? So this curve in this case, so f of x is x squared, this curve itself is a subset of the two-dimensional space, Cartesian space, right? So in this case, the domain is R, real numbers, and the codomain is also the set of real numbers. So in this case, A times B is R squared. And the graph of F for this case is AB, where A is a real number and B is A squared, right? So if we just plot this set on this two-dimensional space, you get this curve. So this is the graph. Okay, now let's consider some of the properties of the graph, which is a subset of this Cartesian product space. And first of all, for every, okay, we consider some graph of some map. And first, for any element of A, of course, we are considering F from A to B, right? For every element of A, there is some B from which is an element of B, such that A, B, so this is a pair of two elements, is an element of this set. Okay, graph of F is a set, right? Graph of F. Okay, so this is a property of the set graph. And second, if we have two pairs, A, B, and A, B prime in the graph, then we should have, so if these two pairs exist, if these two pairs are elements of the set graph of F, then it implies that this B and this B prime are equal. Okay, if the first element of the pair are the same, then it is necessarily the case that the second elements are also the same. Okay, so that is implied by the definition of the graph. Okay, so we take these two properties of the subset of graph as the fundamental properties, and we can reverse the definition of the graph. Okay, so let's define a graph. Definition. Graph. Okay, and let A and B be sets, and S be a subset of A times B. Okay, then we say S is a graph. Okay, now notice that we don't use any maps here. Okay, there's no map mentioned in this definition. S is simply a subset of the Cartesian product A times B. Okay, then we say S is a graph if it satisfies the following two properties. That is actually these two properties. So one, for all A in A, there exists some element in B such that AB, pair AB, is in this subset S. And two, if there are two elements, A, B, and A, B prime in S, then that implies that B and B prime are equal. So if these two properties are met, then this subset S is called a graph. Okay, what's important here is there is no mention of a map or a function. Okay, so graph is defined on its own right. What is nice about this definition? Okay, without using a map, defining a graph without using a map. What's the point? The point is, if we adopt this definition of a graph, then we can use this graph, we can use a graph to define a map. Okay? So formally, we define a map very informally. Now we can define a map, the notion of map, more rigorously. Okay? So this definition of a graph is very rigorous. Okay? There's no ambiguity. So using this, we can finally define what a map really is. So let's try to define a map. But first of all, let's examine these conditions in more detail. Okay? So first says, for every element in A, there is some B, such that this pair belongs to this. Okay, so this is fine. And the second one, if AB and AB prime, so two pairs, are in the graph S, then the second elements are equal. So that means for every element A, the second element is determined uniquely. So this means uniqueness. Okay, so that is essential for defining a function or a map. So here's the definition of a map. So again, A, B are sets, and S is a graph. So S is a subset of A times B, of course. Is a graph in the second definition, okay, in the sense of the second definition of this definition. Okay, graph in this definition is a graph. Then we can define a rule that assigns an element of B to every element of A. So for any uh, for any element A, there exists a unique element B in capital B. Okay, so we denote, let's denote this unique B by Fs of A. Okay, so B is denoted as this. So in other words, we have Fs of A equal to B. Okay, this S is this given graph S. Okay, so this graph defines this mapping. Okay, so and this is, this B is determined for every element in A. So this defines a map. Okay, so this correspondence is called a map. So this Fs is called a map. That is from A to B. Okay, in this way we can rigorously define a map based on sets like this. Okay, so that's all for this video. See you later.